the 3rd floor of the library. So if you guys haven't checked it out, go for it. Lots of good study tools. And I think they have a bunch of like practice tests and stuff. So which is where I took a bunch of your questions from. Like throughout the PowerPoint, I have a bunch of questionnaires. And they go from that. All right, everybody hasn't done so. Just make sure you grab one of each of the packets and sign in. This might get over a little sooner than the 2 hours, too, so I want to make sure I cover all the material you have to cover, give you some time to come up here and ask me questions and stuff. Just no questions during the PowerPoint, because I always want to go ahead and get through it and everything. And then if you have questions afterward, feel free to come see me or any of the tutors at the ASC. Over here, slideshow, beginning. Okay. Just to give you guys a brief overview of everything that's going on. My name is Mary Higgs. I am a tutor over at the ASC Center. I have a bachelor's degree in chemistry with a minor in physics from UCF. I've been with IRSC now for 2 years. I was actually an alumni from here. I graduated my AA degree back in, oh good Lord, I'm going to date myself, 2008. And hoping to be full-time faculty over here. I teach a couple of physics labs and tutor as well, so that's good. So if you guys are following along with your packet, I tried my best. What I did when I made this PowerPoint was I took information from your packets, this is NLN Physics Review right here. I went from there, and I also took information from the book that we have. So your questions, there's going to be a packet of questions that you guys should have gotten as well. I took some of the questions in the review PowerPoint from that. A lot of them are from the book as well. So it gives you kind of like all these questions are actually from review guides, whether it's from the ASC or it's from the book. So both those being said, if you guys haven't seen the book yet, it's actually from the NLN test. They made the review. So review packet, review book one. So it's definitely going to go over. If you guys want to look at this PowerPoint, we do have it on our ASC website. The best way to find it is to Google search ASC at IRSC. And then underneath that, it'll be test prep. So you go to test prep, and then it'll say NLN. And it has different sections, whether it's for physics, chemistry, biology, different things. I know this PowerPoint is definitely on there. And so the handout that you guys have, it doesn't follow along exactly, word for word. So if you guys are trying to follow along, don't. It's going to be more like a general guideline. So, like for example, under Newton's laws, there's going to be a section for that. If you want to just flip to that section maybe and kind of like browse through it while I'm going through the PowerPoint, that might be helpful to you guys. But just don't take it verbatim. These worksheets are kind of like extra information to the PowerPoint in the lesson. So there's that. I tried breaking this up because it is a lot of information. It's a lot of like brand new stuff for a lot of you guys. I tried breaking it up with lots of videos, so to kind of give your mind a break and me a break and hopefully give you guys different learning tools to go ahead and get all this information in. All right, let's go ahead and begin. This is the National League for Nursing RN pre-entrance exam in physics. There's going to be a couple of sections that we're going to be discussing right now. I have vectors, mechanics, Newton's laws, waves, optics, electricity, and magnetism. Those two kind of go hand in hand because an electron is both a particle and a wave, and it travels, it has properties of such. And also thermodynamics is the last one. So the first part is the vector. And what is a vector? A vector is a quantity which has magnitude and direction. We're going to get into that here in a little bit. So there's two types of quantities out there we consider in physics. There's scalar quantities and there's vector quantities. A scalar is going to be an amount or magnitude only, and a vector is going to have direction and magnitude. Now, what is the difference of this? The difference of these is a good example. If you're driving in your car, and your car is going to tell you you're going 60 miles per hour, all right? That doesn't tell you whether you're going to Orlando or to Miami. It just tells you you're going 60 miles an hour. Now, if you add a direction to that, 60 miles per hour north or south, that would make it a vector quantity because it gives it direction to that magnitude. An example I have up here, the pictures, is weight versus mass. So if I have this ball, and it has some amount of particles, right? It's some kind of an amount of stuff, and it has a weight to it, all right? According to here on Earth, weight is determined by the force of gravity pulling it downward, which we call gravity, 9 meters per second, right? So if I put this ball, the same exact ball, and I take it and put it on the moon, I put it on a scale, it's going to weigh less because the gravity of the moon, the force of the moon pulling this object down to the ground is less. I think it's like 5 point something. I could be wrong. Don't quote me on that. But it's pulling it down and it makes it way less. So therefore, mass is a scalar quantity. It's just an amount. Weight then would be a vector quantity because it's the direction it's pulling it down, pulling this mass downward. So speaking of speed versus velocity, there's a nice picture over here which says the speed is the distance traveled and the velocity would be the direction it's also traveling. And of course you have acceleration in your car. We know we can accelerate or we can decelerate. That's going to show whether you're gaining more speed or losing speed, aka direction of where this is going. So distance versus displacement. So once again, if you're in your car and you have to go from your home to school, and you take, some roads over here, and it takes you 5 miles on your odometer to get from your home to school. Now, that's your distance you're traveling. That's what your odometer is reading. Your displacement, however, would be a direct path between those 2 points, between your home and the school. So that's the difference between distance and displacement. Distance is considered how much ground an object is covered during its motion, and displacement then would be how far they are apart from each other. So just a little bit about vectors. So a vector has magnitude and also has direction, aka the length or the direction is the angle with respect to the horizontal. The initial point is termed as where it starts. The terminal point, by definition, is where it ends, the initial and the terminal. All right? One of the questions I saw in the PowerPoint was a standard position. So a standard position is whenever you have a vector and it's located at the origin, right here. So once again, this would be the direction of where the vector would be to remember the angle. And then this would be your vector quantity. So when you have your vectors, you usually add them whenever they are tail to tail. If you have two vectors, so they're right over here. And subtracting would be from tail to tail. Now, vectors, you've all heard about these things in math, but what do they mean in physics? Like, what actually goes on? Okay, now we're kind of getting into like the heart and soul of physics. What we have here is what's called a force diagram. A force diagram takes your object and it depicts with arrows what direction and magnitude something's acting on this. So, for example, I have here your applied forces and your resultant forces. The resultant force is going to be all of these forces added up. We'll take them example by example. So, for example 1, you have a cart, and you have something with an amount of 10 newtons pushing on it. You have another thing like a rope, for example, pulling on it with a force 20 newtons. Both of those forces are going in the same direction, and they're both making this cart go, whether it's being pushed or pulled, with that same force, that same direction. Therefore, the total amount of force acting on that cart would be 30 newtons, because it's all going in that same direction. All right? So the example over here is this one. So you have that same cart, You have a force of 20 newtons, like let's say they're playing tug of war with this cart. You have 2 people on this side pulling on it. You have 4 people on this side pulling on it. Who's going to win? This side with 4 people, right? Exactly. Which is the resultant force of 2 people. What that says in math, so you have your main force is going to be equal to your F1 plus your F2, which is that formula right up here in the PowerPoint. If you're looking at this, which is example B over here, or example A, I'm sorry, as far as, consider like a number line, you have your vectors starting in the standard position at 0. You have one that's going 40 points on the positive x direction. You have another vector which is going 20 points on that negative x-axis. We can consider this F1 and F2. So F1 would be at a negative 20 because on the negative x-axis. And then the 40 is going to be in the positive x-axis. So then your total is going to be 20. And that's where they get that from. So the same thing in the next example down, letter B, where it's going to have the 2 forces. So you have 25 people pulling it one way, 20 people pulling it the other way. And it's the same amount of force they're pulling on it from either direction. This thing's not going to move, right? So if you want to consider this as your origin at 0, so you have a negative 25 and you have a positive 25, they're going to cancel out to have your resultant force, overall force, being 0. Okay? Not too bad. You guys will all be physicists by the end of this, I promise. Okay, so friction. Friction is something that's going to oppose the direction of motion. Friction, if you're drawing on a force by diagram, is always drawn opposite the direction of motion. So it only applies to solids, and a resistance is going to occur in gases and liquids. So for example, going back to like one of these cart examples over here, let's say we're using this as our example. And this next thing, where you have 10 newtons and you have 20 newtons. This is how it should be drawn in a force diagram. You have your force 1 going in this positive x direction. The force 2 is also going as positive x direction. Then you're going to have friction, like let's say that this cart's rolling on like a rocky surface. So there's resistance there, there's friction between those wheels and then, you know, that cart. So it's going to cause friction. Now, what's going on with this normal force and this weight? What you're going to learn later on from Newton's laws is that everything has equal and opposite reactions. So this ball is sitting on my hand because my hand is able to hold the ball, right? If I were to put, I don't even know, 2 bowling balls on my hand, I probably couldn't do this. It's probably going to my hands are going to have enough force to push up against those bowling balls, and I'm going to drop it. So for as much weight as that object exerts onto a contact surface, the contact surface then also pushes up the same amount of force to be able to keep it at the equilibrium. So we're going to learn about that here in a second as well. So your normal force is the force that's pushing up from the contact surface onto your object. And your weight, of course, is the weight of whatever the object is, which is gravity pulling it down. Because everything has a weight. So this is another example of a force diagram. You're going to have your normal force, which is the force of the ground pushing up against this object. You have the force due to gravity, or its weight. They're the same, they're synonymous, pulling it down. You're going to have friction if there is friction. Friction is always drawn opposite the direction of motion. And this applied force is what's going to be pushing or pulling it forward. Okay? So your gravitational force is, of course, going to vary with mass. Because force that we're going to learn is going to be equal to mass times acceleration. So if your weight is a force and force is a mass times acceleration. Your acceleration is due to gravity, which is what's pulling it down. So therefore, force due to gravity is your mass of your object times your acceleration, which on Earth is 9.8 meters per second squared. Okay? Perfect. All right, so all moving objects are also going to have momentum. Momentum is defined in physics as mass times velocity. Now, the conservation of momentum is a pretty important concept over here in physics. I'll read it to you. It says the total momentum of an isolated system is always constant. During a collision between two bodies, the momentum of each body changes, but total momentum is conserved. All right, now what does that mean? There's an example over here of pool balls. So you have a pool ball sitting there, and we're going to consider this a frictionless table for the purposes of the concept. So you're going to hit this cue ball into the yellow ball. The yellow ball's sitting there still. What's making the yellow ball move? The white ball, right? So the harder you hit that white ball into the yellow ball, it's going to move farther or not as far, depending on how hard you hit that white ball to go hit the other ball. And that's what the conservation of momentum is. It's that transfer of energies, basically, from one ball to the other. All right, so here's a question from your questionnaire about weight and mass. So, which of these statements are correct? Weight and mass either represent the same data, are the same, are the result of an external force, or are different? Correct. D, they're different. Because once again, mass is the amount of stuff you have. Weight is the result of a force or gravity, acceleration due to gravity, on the object. There's a picture for you guys. So next question. A vector is in standard position when the initial point is at the origin along the x-axis, in the lower left quadrant, or along the y-axis? At the origin, correct. Awesome. So, the law of conservation of momentum states, mass has no effect on momentum, velocity is dependent on momentum. Without outside forces acting on moving objects, the total momentum remains constant or none of the above. Correct. See, you guys are all doing so good. You're like physicists. It's awesome. Yeah, there's an example of Newton's cradle. I don't know if you guys have ever seen one of these before. Most teachers have them like in their room somewhere. But the cat's cradle. So if you guys haven't seen one of these before, what happens is you pick one of the end balls up and you raise it up some certain distance. And you let it fall, and it goes through and it hits all the little balls, and then the one on the very end of that one flings back up, and then it just kind of continues. One hits the other, one hits the other, one hits the other. That's considered conservation of momentum. Because the same way with that cue ball, whenever you take it, and it depends on how hard you hit that, that's going to affect the yellow ball moving. The same way with this. So if you take that, your first initial ball, when you raise it up, if you raise it only a little bit, this one on the very end is going to only move a little bit. If you raise it all the way up really high, the other one on the other side is going to go up really high too. So that momentum is conserved throughout the entire pendulum. So mechanics. Mechanics are the study of motion. All right, so we have machines, simple machines. Machines, what they do is they just make work easier. You guys have a little handout from that that they made the ASC about simple machines. Well, all in all, through all of our tools, there's 6 basic machines of what we use today. So you have inclined planes. The example is a person pushing a box up a plane instead of having to go pick this heavy box up and pushing up and moving it. If you have to go move this really heavy thing, you can just like push up an incline and it'll make it easier, right? A wedge. We use it for an axe. You're taking that force and you're pulling it down, and it's putting all that force into one tiny point, and it's able to split wood, for example, like this axe. A lever. I know I couldn't pull a nail out of a piece of wood myself, but this hammer is. It's using the torque from the lever. Wheel and axle, example is going to be like a doorknob. Screws, like a jar lid, and then pulley systems, of course. Now all these types of machines that we have designed to help us out. So we can have an example of a compound machine, like a scissor. So scissors are going to contain wedges and levers to make a scissor work. So it's taking all that force from your hand and it's compacting it into little slices. So it's always important to know that no machine can ever be 100% efficient due to friction. Some energy is always going to be lost, and that's mostly going to be due to heat. And efficiency is defined as the ratio of work in to work out. All right, now here's a bunch of stuff here. All right, so the important part with physics, like I said, there's not many equations, not much math that I saw on your test. It doesn't get anything crazy. These are important ones to know, though. So the example I have here, before I get into the equations, is a ball and it rolls down a hill. When it starts up here at the top, it's going to have potential energy. It's going to come down here to about halfway where it's rolling. It has potential and kinetic energy. It rolls down to the bottom, and it's still rolling, so it's only kinetic energy. So finally it rolls to a stop, and it has nothing. It's been lost. Now, what do all these energies mean? These energies are going to come from these two equations over here. Notice that the kinetic energy, abbreviated KE, is considered work in motion. Now, why is that? The equation reads that's 1/2 mv squared. 1/2 is a number that's never going to change. If I have this ball and I'm moving it from here to a different position, does the mass of this ball ever change? No. So therefore, the mass of this object is constant. Therefore, the only variable is how fast or how slow this ball is moving. So therefore, kinetic energy is determined by velocity or speed. Potential energy, once again, reading that equation, it's called mgh. So m is going to stand for mass. Once again, the mass of this ball is never going to change. G is gravity, and as long as we're staying here on Earth, it's going to be constant. It's going to be 9.8 meters per second squared. And then you have the h stands for height. Now, is that a variable? Whether the ball is up here or the ball is down here, correct? Correct. So therefore, potential energy depends on height. So going back to the example I had of the ball right down the hill. As it sits here on top of the hill without it moving, it's not moving, so there's no kinetic energy. It has potential, though. So as it rolls down, it's going to be moving. Therefore, it has a velocity or speed, so it has kinetic. It still has a height, though, because it hasn't hit the bottom yet, so it has potential as well. It has both. It rolls down to the bottom. And at the bottom over here, it no longer has a height, so it never doesn't have any potential energy. But it is still rolling, and it has a speed, so therefore it has kinetic. And finally, when it rolls down to a stop, it's going to have neither kinetic nor potential energy, which means that energy has been lost due to heat or different types of energy. It's been pushing, because energy is like never lost. It's always cannot be created or destroyed, so it's always conserved. Important to know that energy is measured in joules, and a joule, whenever you break it up into its components, it's considered Newton meters. Now, I don't know if you guys learned this or not, but scientists are really lazy. You guys are probably seen this in the medical field, where everything's abbreviated and everything's down to its shortest thing it could possibly be. Physicists are no different. So instead of writing out Newton meters, we just consider it a J for joules. And that's what energy is termed in. All right. So going back down to over here, it says work. So the formula for work is force times the distance, which means that any time that you are moving an object, you're putting force on it, you're doing some kind of work. Whether I'm lifting an object up or down, you're doing some kind of work. You're moving it and you're giving it force to move it. And power is termed as the rate of what you do work. All right, here's a short video for you guys.
Mr. Anderson, and today I'm going to talk about potential and kinetic energy. Remember from the last podcast that energy is the ability to do work, and work is a force times the distance. So we measure work and energy both in joules. Now there's a law of the conservation of energy. In other words, that law states that energy can neither be created nor destroyed. Now it can be converted into mass according to E equals mc squared, but we'll get to that later. And so since energy can neither be created nor destroyed, it can be converted. And so the two terms that we generally talk about when we talk about storing or using energy are potential and kinetic energy. Now I'm talking about potential gravitational energy and kinetic energy. And so we also have potential energy, for example, in the chemical bonds of a molecule, but I'm not talking about that. And so the two types of energy that we have are potential energy, and that's energy due to position, and kinetic energy, and that's energy due to motion. And we have equations for each of these. Potential energy is mgh, where m is mass, g is gravitational acceleration, and h is the height. And then kinetic energy is 1/2 mv squared, where m is mass and v is the velocity of the object. Now the best place to look at how energy is converted from potential to kinetic energy is in a pendulum. A pendulum is simply a weight attached to a string. And so if I hold a pendulum at one side and don't let it go, it has a certain amount of potential energy. When I let it go, the pendulum will swing back and forth. That energy is converted from potential to kinetic, and then back to potential energy, and then to kinetic, and then potential, over and over and over again. And so when that ball is sitting at the top, it has all potential energy. When it's at the bottom, it's converted all of that energy into energy of motion. And so when it's halfway down, we would say that it has a combination of potential and kinetic energy. And it's just converted. Now, will a pendulum swing forever? No, because we're going to lose a little bit of that energy in friction, in heat, in sound as it moves. And so eventually that pendulum is going to come to a stop. And so let's do a couple of problems with potential energy and kinetic energy. Potential energy, remember, is measured as mgh, where m is mass, g is gravitational acceleration, and h is height. And so let's say, for example, that I climb to the top of a 10-story building. And so first of all, we have to know my mass, which is 78 kilograms. We have to know the acceleration due to gravity, or g, which is negative 9.81 meters per second squared. And then we have to convert that 10-story building into meters. And so a 10-story building is roughly 32 meters high, or that's our h value. And so if we simply multiply those all together, we get 24,485.76 joules, and if we do significant digits, that's 2.4 times 10 to the fourth joules of energy that my body has at the top of a building. And as long as I stay at that top of that building, I can use that on the way down. I don't want to jump off the top because I don't think I'd be able to make it. The next type of energy is called kinetic energy. Energy of kinetics, or motion, is 1/2 mv squared. And so that's energy due to motion. And if I jumped off a 10-story building, I would convert all of that into kinetic energy at the bottom of my fall. But I don't want to do that. And so let's do one dealing with a baseball. Let's say I pitch a baseball, and there are two different pitches. When I throw a baseball, I probably throw it around 20 miles an hour if I were to throw it. I'm not a very good thrower. But a really good major league pitcher will throw it at 100 miles an hour. And so let's figure out how much kinetic energy would be in one of my throws and then those of a pitcher in the major leagues. First of all, we have to figure out the mass of the baseball. Mass of a baseball is 0.145 kilograms. And since we're doing kinetic energy, the only other value that we need is the speed. And so if you throw a 20-mile-an-hour pitch, that's roughly 9.0 meters per second. Remember, on all these, we always have to convert it to meters, or meters per second, excuse me, if it's a velocity. A 100-mile-an-hour pitch, then, is roughly 45 meters per second. And so first of all, let's figure out how much kinetic energy my pitch would have, a 20-mile-an-hour pitch. We use the equation 1/2 mv squared, where m is 0.145 kilograms and v is 9.0 meters per second. We then take that times 1/2 and square the velocity, and I get, using significant digits, 5.9 joules of energy. Now let's try the faster pitch. It's 100 miles an hour, so that is 45 meters per second. So we're going to use 1/2 mv squared. Our mass remains the same, or it's 0.145 kilograms, except our velocity now is 45 meters per second. If I multiply that across using significant digits, I get 150 joules of energy. Again, when I pitched at 20 miles an hour, it was only 5.9 joules. And so even though that pitcher is throwing it 5 times as fast, he's getting roughly 25 times the amount of energy out of that pitch. And that's why, if you look at the equation, the velocity being squared is super important to understand that. And so you can solve complex problems now that you know the equation for potential energy and kinetic energy. For example, in class, we figured out, based on the speed of a sprinter and the mass of a sprinter, you should be able to figure out how high they could pole vault if all of that kinetic energy were converted into potential energy at the height of that vault. But that's it. That's, in summary, again, the ways that we can measure energy in joules, and it's the ability to do work. And remember, it's always converted from potential, or energy due to position, to energy of motion, or kinetic energy. I hope that's helpful.
Awesome. So now we know everything about energy. That's awesome. Good, good, good. Okay, so another kind of weird one I saw a little bit, it just touched on briefly, was Hooke's law. So Hooke's law is defined as force equal to negative kx. I don't think it's in your packet, but just to touch on it real quick. So k is considered the spring constant. X is the distance the spring is stretched or compressed. So it's going to go through like a little, literally minute-long video that shows you this whole thing. But all it is just describing this. The force of a spring determines on how much has been compressed, and it's in like a big, like what's that stuff called? Not ping pong. Those are little arcade machines where you take the ball and it goes through. It goes little flappers. What's it called? Pinball. Pinball. Thank you. Yeah. So you take that little spring back and it shoots that ball off. That's going to be giving that ball force of the spring. Also, if you take a string and you go and like you stretch this spring down and you kind of let it go, it's going to brush it out too. So that's that.
Elastic objects such as a spring can store elastic potential energy when they are stretched. For example, this happens when a catapult is stretched back. When an elastic object such as a spring is stretched, the increased length is called an extension. The extension of a truly elastic object, again such as a spring, is directly proportional to the force applied, provided the limit of proportionality is not exceeded, meaning the object being stretched doesn't become permanently deformed, such as when a spring doesn't return to its original position after the load is removed. This proportionality is called Hooke's law, and the force is equal to the spring constant times the extension. The spring constant is measured in newtons per meter and is different for different objects and materials. You work it out by carrying out an experiment with an elastic object and adding a load or force to it. You then measure the extension of the object and sub the numbers into the formula to get the spring constant. The greater the value of K, the stiffer the spring.
All right. There's that. Okay, so come questions. So, machines may be used for all the following purposes except to multiply force, increase energy, transform energy, or multiply velocity. To increase energy. They can't increase the energy that you're putting into it. You're putting the energy into it. All right, here's another kind of trick question. So you have a mom and you have her kid. They're going to be lifting identical bowling balls from the floor to the top of a table. So the mom or the child, which one did the most work? Mom, child, both, or none of information? See, good job, guys. Yay. Because remember that work is only equal to the force times the distance. It doesn't matter who's doing the work or doing the force of lifting. It just matters the force that's being able to lift the ball up. Okay, good job. So, Newton's laws. Newton is a really cool scientist. He's English. He invented calculus, the telescope. He has a bunch of these like really cool ideas that got turned into Newton's laws. There's 3 of them, and they were going to control physics for the next 3 centuries. Basically up until Albert Einstein developed his theory of relativity, which is a whole other concept in itself. This is what defined physics. They were also able to determine that these laws exist in space, so they're actual laws. They don't change. So the first one is the law of inertia, which basically says an object in motion continues in motion with the same speed and the same direction unless acted upon by an unbalanced force. That just means objects want to keep doing what they are doing. If this eraser, if it just sits there and nothing happens to it, nothing's going to happen to it. It's not going to get up and just move on its own. A force has to act on it in order for it to do anything. If I push it, that's going to be putting a force into it, and it's going to be able to go move. Now, in space, in a perfect world, if I were to take that eraser and I were to push it, it would keep going on until something else stopped it. But there's things like friction and air resistance and stuff in our world, so it makes things stop. Next one is basically force equals mass times acceleration. Once again, reading these equations. A force is going to be equal to the mass of an object times acceleration. So there's a nice picture over here, which has somebody pushing a cart. He's pushing an empty cart, and he's able to go, if you're in a grocery store, it's not going to take much force to get that thing moving. If you then throw a couple of cases of soda in your cart, it's going to weigh it down a little bit. It's going to take more force to get that cart moving at that same acceleration. So if you're just going with the same force that you're using with an empty cart, it's going to be moving slower, because you have to go put more force on it in order to get that cart up to speed again so you can finish your grocery shopping in time. Now, the third law says that for every action, there is an equal and opposite reaction. Now, what does that mean? If I have, remember I said before, how all contact surfaces, they push up against an object. So I have this tissue right here, and it's holding this marker. It's able to hold the marker because the marker is light enough to be on the thing, aka the weight of the marker pushing down on this tissue, the tissue is able to put enough force back up onto the marker. So therefore it's able to sit here in equilibrium and be happy and balanced. Now, what would happen if I were to take something heavier, like this Gatorade bottle, on this tissue? It's eventually going to rip through this tissue paper, right? Because it's too heavy for it. What that says is that this Gatorade, as it's pushing it down, is pushing down with more weight. If you draw this like on a vector diagram, your weight of your Gatorade bottle is more than the force of the tissue is able to push back up. So therefore, it's gonna, your downward force is going to win, and it's going to end up breaking through this and going down. So there's that. Another video on Newton's laws.
Did you know that physics is about how things move and why things move? It was Isaac Newton who discovered the 3 laws of motion. He was a scientist who lived from 1642 to 1727. Let's first learn about the first law of motion. It is also called the law of inertia. It states objects will remain at rest or in uniform motion in a straight line unless acted upon by an external unbalanced force. To understand Newton's first law completely, we need to learn about inertia first. See, this is a very large sofa. What's special about it? It's stable. It is not moving. Now go ahead and try to move it. Oh, you can't. It's not willing to move. You can't move it as it is very large. Now try to move this small stone. Good. You can move it a little bit, but you had to put in a lot of effort. It was also like it didn't want to move from its original position. Even the smaller things don't want to change their positions. They don't want to move. Even a small stone takes some effort to move. This is the first rule of physics. Things like to stay where they are. No object in this universe would start moving unless some external effort is put on it. It's like all things in the world are lazy. Now the question is, if things are lazy and they don't want to move, then how does the movement happen? The answer is that there are so many things in the universe which push and pull other things and force them to shift their positions, like you force the small stone to move. But as we said earlier, that things are lazy, they would try and stop their movement as soon as the effort was removed. Well, you'll be wrong if you think like that. You'd find it very strange to accept that when a small stone was still, it wanted to stay still. And once you'd put it in motion after putting some effort, it would like to keep on moving. In reality, it would keep on moving forever and ever. But somehow it stops. But it stops not because it wants to stop. It stops moving because things in its path force it to stop. It may be due to air, or if it bumps into a tree or rough surface on the ground. But suppose there were no tree in its way, or there was no roughness on the surface, and also imagine that it does not have poles or trees in its way. The stone would never stop. It would keep on moving. It happens in outer space, where there's no air or roughness. If you kick a small stone, it'd keep on moving and would never stop. So how can we say that things are lazy? See, the small stone wanted to move forever, but it was stopped by the resistance of air, trees, or roughness of surface. It's like you moving on a slippery road. You'd keep on moving unless there was some effort put in to stop you. The same is true with the small stone in outer space. It would keep moving, as nothing came in its way. It also doesn't want to stop, as it is too lazy to do that. So now we can change the first rule of physics. Things want to stay in the position they are, to things want to keep doing what they're already doing. If things are at rest, they want to stay at rest. And if things are moving, they want to keep moving. In other words, things are lazy. So there's a lot of laziness in the universe. Physicists have a special name for this laziness. It is known as inertia. So now you understand Newton's first law of motion. Can you write it? Well, you are very much right. Now let's move on to Newton's second law. As we know from the first law that to overcome the inertia of an object, we have to apply unbalanced force. Newton's second law talks about how fast an object would move. Well, it states acceleration of an object depends on the mass of the object and the amount of force applied. In mathematical terms, Newton's second law states that force is the product of mass and acceleration. To cause an object to accelerate or speed up, a force must be applied. The more force you apply, the quicker you accelerate. Look at these two swings. If you apply the same force on both swings, check whose goes faster. Let's first push the little kid. See? It goes very high. Now push this fat man with the same force. See, it does not go far, because it has more mass than the little kid. So the more mass there is, the force required to push the object is also greater. Let's look at the mathematical formula of the second law again. It's the product of mass and acceleration. We've already learned that if there's more mass in an object, to move it, we need more force. Now let's see this kid sitting in the swing. If we apply little force, then it goes a small distance. Now if we apply a lot more force, it goes very high. So to get more acceleration, we need to apply higher force. So now you can understand the relation among force, mass, and acceleration. Until now, we've only learned the first and second laws of motion. Oh, you're riding a bicycle. Have you ever wondered why a bicycle moves forward? Well, it moves according to Newton's third law, which says that for every action, there is an equal and opposite reaction. To understand this, see what happens when you drop a tennis ball. As the tennis ball hits the floor, it causes a downward force on the floor. This is the action. The floor reacts by pushing on the ball with the same force, but in the opposite direction. Action, reaction. Together, the floor and the ball form what's called the action-reaction pair. So now how it applies to your bicycle. When you push the pedal, the parts of the tire which touch the ground push it backwards. The ground also pushes the tires forward with the same force. So the parts of tires and earth form a pair of action and reaction. So what happens to the earth when your tires are applying force to push it backwards? Nothing happens to it, since the earth is very big as compared to your bicycle. The force applied by your tires does not move it backwards, but force applied by the earth pushes your bicycle forward. So now you understand Newton's third law. Yep, the tennis ball is the right example. The ball and the floor are creating a pair of action and reaction.
All right, there's that. Okay, a couple of questions on Newton's law. So Newton's law is used in the study of mechanics, electricity, thermodynamics, or optics. Mechanics, correct, the section we just covered. Awesome. Okay, so here's a little bit of a math problem for you guys, and I want you to do it yourself. So you have a force of 5 newtons causes an object to accelerate at 5 meters per second squared. So what is the mass of the object? So I'm going to work it out with you all. All right, so it's F5, A5, okay. All right, coming over here. So we know that force is going to be equal to mass times acceleration. So if our force is going to be equal to 5 newtons, the mass, what we're trying to figure out, the acceleration we said is 5 meters per second squared. Just plugging those in. Therefore, our mass is going to be equal to 1 kilogram. And just an FYI, that's like the extent of the math I saw on this NLN practice quiz. I don't think it should get anything much harder than that at all. The other equations I had up there were simply just so you can understand the principles of what was going on, but as far as math goes, that's about it. So, not too bad, right? Okay, so waves. Waves is a disturbance that flows through a medium. That medium could be air, that medium could be water, basically anything. So there's 2 different types of waves. There's transverse and longitudinal. Transverse waves are going to be vibrating at a right angle to the direction of travel. So think of transverse waves as you dropping a stone into water. You're dropping a stone straight in, and those ripples are going to be going outward at a right angle. Longitudinal waves, however, are going to be vibrating along the path the wave travels. So if I start yelling, if you yell, you can hear your voice being projected this way. The people on this side of the room are going to be hearing me a lot clearer than this side of the room because it's going on the direction of travel. All right? Parts of a wave. So there's different parts. Think about it as like reading like a monitor whenever you guys are in the hospital. So you're going to have your amplitude, which is your maximum distance the wave rises or falls. The amplitude is going to be these peak, right? It describes the amount of energy the wave carries. So it's going to determine your brightness or your loudness of the wave. Your frequency is going to be how fast it's going to be propagating. So a period is just this little wavelength over here from start to finish, and how far it's going to repeat itself. Now, the electromagnetic spectrum. The electromagnetic spectrum is very, very broad, and it's a certain type of wavelength or frequency. So it goes all the way from gamma rays through X-rays, UV, visible spectrum, infrared light, microwaves, radio waves, and then just radio waves. All right? Notice, though, how the increasing frequency and the increasing wavelength are different. So a lot of times, physicists will consider things going to a blue shift or a red shift. If you consider your visible spectrum along this entire scale over here, your blue shift would be more of a fast, rapid movement, and the red shift would be more of a slower, more lenient shift. All right? An electromagnetic wave is a special kind of wave. It's going to be a pair of transverse waves that are going to be carrying charged particles like light or microwaves, etc. So the motion of them is going to be perpendicular to the direction of the wave in motion. The Doppler effect is an interesting principle. So it says that the change of frequency of a wave in relation to the observer moving relative to the source. So the example over here is that if you have a police car and it's coming at you, you're going to hear that siren, and it's going to be like really, really loud, and as it passes by you, it kind of like fades off. This is because of the way the sound is traveling. So the sound is traveling initially at really, really fast speeds over here at a higher frequency, and then as it goes out, because the car is moving, those waves then are a little bit slower, a little more spaced out. Therefore, it just sounds like a little bit lower frequency.
The Doppler effect. In Sheldon's words,
it's the apparent change in the frequency of a wave caused by relative motion between the source of the wave and the observer.
The Doppler effect is perhaps best explained visually. So here's a thing that is emitting waves. It could be a fire truck emitting sound, it could be a star emitting light, it could be a duck creating ripples on a pond. Those are all waves, and they all look something like this. We see the Doppler effect happening when the thing that is emitting waves moves. In the direction it's moving, the wavefronts bunch up, and behind it they spread out. If our object is moving towards a stationary observer, these bunched up waves are observed at a high frequency, and if the object is moving away from a stationary observer, the waves are observed at a lower frequency. So that is the Doppler effect, the apparent change in the frequency of a wave caused by relative motion between the source of the wave and the observer. It makes sense, but it gets interesting when you consider some of its applications. So let's say you are standing in the middle of a road. That's you, and a car drives past you very fast. As it does so, it honks its horn, because you're standing in the middle of the road. The horn to you might sound something like this. So it starts at a high pitch and moves to a lower pitch, even though from the driver's perspective, the horn is playing the same pitch the entire time. So what's going on? As the vehicle's coming towards you, the sound waves that it's emitting bunch up, and so are delivered to you at a higher frequency, which you interpret as a higher pitch, because the frequency of sound waves is pitch. And then when the vehicle passes you and is moving away from you, the sound waves spread out, and so you hear them at a lower frequency, a lower pitch. So that's how the Doppler effect works with sound. It also affects another kind of wave, light. So let's say you look out your observatory and you see a star. Just like the car's sound waves, if the star is moving towards you, even just a little bit, the light waves that it emits will be bunched up, meaning that you see the light at a higher frequency than it actually is. Frequency in sound is pitch, so what does it mean for light? Well, if we look at our handy pocket electromagnetic spectrum chart, we'll see that a small change in frequency for visible light will change its color. Higher frequency light waves means bluer light, and lower frequency light waves means redder light. This is called redshift, and it may possibly be among the weirdest and coolest things of all time. Stars, or anything that you can see, change color depending on their relative motion to you. Of course, you can't see this minute difference with your eyes, but astronomers with the right equipment can use this effect to tell whether stars are moving away from or towards Earth. As it turns out, almost everything we can see in the universe is moving away from us very quickly, which is both an important piece of evidence for the Big Bang and an indication that the Earth might get very lonely in the distant future. Thanks for watching this video. Let me know if you got something out of it. Bye.
So that's kind of cool, though. It kind of shows how a lot of things in physics, they affect different principles. So like how you saw Doppler effect isn't really affecting sound, it affects light. Those are all waves. So stuff's really cool. It affects everything you do. All right, so one of the questions. The number of complete waves passing a given point per unit of time is considered the frequency, the crest, the wavelength of the period. Number of complete waves. Frequency, correct. All right, there's a little picture of different kinds of frequencies. So the electromagnetic wave can be represented by, so the entire spectrum, is it going to include microwaves, sound waves, X-rays, radar, A, B, and C, or none of the above? E, correct. So the electromagnetic spectrum, once again, is going to contain this wide range of different wave types, whether it's light, sound, through the radio, different types. So optics is the behavior of light. As you see here, we have a white light going into a prism, and that prism is going to be able to break this light up into its different components, like the rainbow. That's because of the different frequencies and wavelengths of each of these colors. As you saw before from the electromagnetic spectrum, each of these colors has its own separate frequency and wavelength. Same thing is going on over here. That's why it's able to separate off. So a study of light. Light is made up of photons. It's an electromagnetic wave, and the speed of light is a constant. It is determined to be 3.0 times 10 to the 8th meters per second. I don't want to be too concerned with that number, just know that it is a constant. We call it C in physics. So light behavior is affected by the medium that it hits. It can do three things. if it hits a transparent medium, translucent, or opaque. Transparent would be something clear over here, like at this nice little glass window, where all light's going to be able to go through, and you're going to be able to see what's behind it because of the light reflecting back behind you is reflecting the giraffe, and that's where you're able to see the giraffe. So translucent is some of the light passes through, so you're really able to see part of that light hitting the giraffe that your eye is going to be able to see. And opaque means your light is absorbed or reflected, which means you can't see anything behind there. So there's no giraffe to illuminate. So when light hits a medium, it can do three things. It can either disperse, reflect, or refract. So dispersion is what we saw over here in the beginning, where it took that white light and dispersed it up into its different wavelength components. So it separated it up basically into different wavelengths, different frequencies. It can also reflect. Reflection would be considered like a mirror. Or if you had anything else that could reflect off of this shiny board over here. Whenever it hits it, it's going to bend back off at the angle of reflection. So also it can refract. Refracting is any time the light bends. If you guys ever see whenever the example over here is water, if you're walking in the water and it kind of looks like your feet are a little bit off from your body, that's why it's called refraction. As the light goes through that medium, the light's going to bend, so your eyes are going to interpret your feet being in a different position because of that bending of the light. So lenses. I want you guys actually all to flip to your packet right now. I want to make a correction on here. On your NLN review packet, if you go to page 6, which is the page with the contact lenses on it. So on letter D, it describes lenses, and it has two sections, section I, section II, 1 and 2. So under convex lens, where it says the lens, whatever, appears smaller, the last word there says smaller, it should be bigger. And then on part 2, it's going to be the opposite. So it's going to say a concave lens causes rays of light to diverge. Images can be larger than the actual object. That larger should be smaller. So let's go ahead and flip those around. This stuff does get super confusing when it comes to different kinds of lenses. So first of all, we have the law of reflection. So the angle of incidence is equal to the angle of reflection. So what that says is if you were to shine some light, like a laser, for example, if we were going to go shine it on a mirror, that light is going to bend off, reflect off, as long as the mirror is completely straight, at the same angle that the laser went in on. So if you had a protractor, for example, in a flat mirror, and you shone a laser pointer at that mirror, it's going to bounce off the mirror at the same angle. So there's the metric. Now, convex versus concave lenses. I found a really good video that describes these. These are super complicated and kind of confusing. So let's get into it.
Okay, in today's video, we're going to talk about how parallel light rays interact with concave and convex lenses and mirrors. So we're going to look at all 4 of those devices and see what happens when parallel rays either strike those mirrors or pass through those lenses. Okay, so the first one we have here is our convex lens. You'll notice it bulges out on both sides. That's what we call a biconvex lens. The second one is the lens that bulges in or is caved in on both sides. This is called a biconcave lens. And what we want to be able to answer at the end of the video is why, when you look at the image of my face through the concave lens, does it appear right side up, but when you look through the image of my face through the convex lens, it appears upside down. So in one case, it's upside down with the convex lens, and in one case, it's right side up with the concave lens. Upside down, right side up. What's happening to the light as it passes through each of those devices to cause it to be upside down, the image to be upside down in one case, and the image to be right side up in the other. And of course, we want to do the same thing with the mirrors. This is a concave mirror. It's caved in on one side. So you'll notice that the image of my computer is upside down. When I pass my hand across the keyboard, you notice my hand comes across the top of the mirror. The image of the computer is upside down. In this case, we have the convex side. The image of the computer is right side up. Why is it that in this side, the convex side, the image is right side up? And why is it that in this side, the concave side, the image is upside down? Okay? So let's go through and see if we can figure that out. We're going to kind of just summarize what we've seen so far. Convex lens, image upside down. Concave lens, image right side up. Convex mirror, image upside down. And then the convex mirror, the image was right side up. So what is the same about these and what is different about them that causes those images to appear that way? And we're going to group these two together. We'll look at these two first. Hopefully something is similar about these two that causes the image to be upside down, and what's the same about these two that causes the image to be right side up, and how is this pair different from this pair, okay? And we're going to do this using parallel light rays. We're looking at an object that is far away, and the light rays are coming in parallel. They pass through that lens, and they're going to be refracted. Now, they're going to be refracted at each boundary, but we can approximate that refraction by showing the refraction or the bending of light at the center line right here. So here's the object. The light rays are passing through the lens, and you, with your eye, are looking at that object. You look at the object through the lens, and what happens is the light rays, when they come through that lens, they are refracted or bent in such a way that they all pass through a single point. That point is known as the focal point. Okay? They converge, and therefore we call this lens a converging lens. And you'll remember, as long as the object is far away, is beyond the focal point, the image will appear upside down, or what we call inverted. So the image is inverted. Okay, so a convex lens is also known as a converging lens, and the image most of the times will appear inverted. We'll talk about when it can appear right side up in future videos. Okay, let's do the same thing for the concave mirror. This is the shiny side, the concave side of the mirror. There's your eye, you're looking at an object, maybe it's your face you're looking at, or some other object like my computer in this case. You'll notice the light rays come in parallel. They strike that mirror, they're reflected in this case, and they're reflected in such a way that they all, once again, will pass through the focal point. They converge at the focal point. These converge at the focal point, these converge at the focal point. Therefore, we call this a converging mirror, and the image appears inverted. And as long as the object is beyond the focal point, then the image will appear upside down. If we bring the object inside the focal point, then something different happens, which we'll talk about at future videos. Then it will appear right side up. But for parallel light rays that are coming in from greater than the focal point, the image, the light rays converge at the focal point, and the image is inverted. If they're coming in parallel, they're going to converge at the focal point, and the image appears inverted. Okay, so you can see we have the opposite shapes: the convex lens, the concave mirror. They're both called converging devices. This is a converging lens, a converging mirror, and the image is going to be inverted or upside down. Okay? Now we're going to look at the concave lens and the convex mirror. And in this case, once again, light rays are coming into the lens. They're going to pass through the lens. In reality, they get refracted at each boundary between the air and the lens, but we can approximate that refraction by showing it refracting at the center line. Here's your eye, you're looking through the lens at the object, the light rays are coming through the lens towards your eye. But in this case, after they pass through the lens, or as they pass through the lens, they're going to be bent in such a way that they diverge. So they're going to move away from each other. They don't converge, they diverge. Therefore, this is called a diverging lens. The concave lens is a diverging lens. Now, how does your eye or your brain form an image if those light rays are moving away from each other? They have to cross or intersect for an image to occur. But what happens is your eye does not know that this bend occurred. It does not know that this refraction occurred. It assumes the light rays traveled in a straight line. If these light rays are followed back by your eye, by your brain, you'll notice that they appear to come from the focal point. Do they come from the focal point? No, they do not come from the focal point, but they appear to come from the focal point. And therefore, we get what we call a virtual image, which we'll talk about virtual images in a future video also. Okay? But a concave lens is a diverging lens, and the image appears erect. And in this case, the object, regardless of where it's placed, will always look right side up or erect. Okay? This is a diverging lens. The rays are bent in such a way that they appear to come from the focal point. So when you bend these, you have to bend them with your ruler so that you can draw them back to the focal point. They all have to look like they're coming from the focal point. Do they come from the focal point? No. Okay, that's the definition of a virtual image. Okay, now let's do the same thing with the convex mirror. Here's the convex mirror. It's shiny on this side where the light rays are coming towards it. The light rays strike that mirror, and what happens, they're going to be reflected. And how they're going to be reflected? They're going to be reflected so that they diverge away from each other. So a convex mirror is also known as a diverging mirror. Now what happens? How does your eye form an image from this mirror? Okay, your eye is taking those light rays in. It does not know that they changed direction or were reflected right here, so it assumes that they traveled in a straight line, and they will appear, once again, to come from the focal point. So students often ask me, well, how much should I bend these? Okay, they diverge, but how much do they diverge? They have to diverge just like these so that they appear to come from the focal point, so that they can be drawn straight in a straight line back to the focal point. The focal point for a diverging mirror is behind the mirror. Okay, the light rays appear to come from behind the mirror. Do they actually come from behind the mirror? Of course not. A mirror is a solid image, solid object. You cannot see through a mirror, but your eye thinks that they come from a mirror. Now, if you look carefully at this mirror, you can see that it looks like, I think it looks like to you, and I think I can see it too also when I look at it, that the image is behind the mirror. Is it really behind the mirror? No, it's not. Okay? So it looks like it comes from behind the mirror, but they do not. That is, again, a virtual image. And regardless of where we place the object will always be right side up and it will always be a virtual image. Okay? So let's just summarize this page. Concave lens, convex mirror, opposite shapes. They're both diverging. Therefore, the image in both cases is going to be erect or right side up. Okay, so that's the difference. In one case we have a diverging device, in the other case we have a converging device. And we can summarize all that information right here. Convex lens, converging. Concave mirror, converging. Therefore the image is going to be right side up most of the time, not always, okay? Most of the time, as long as we're beyond, as long as the object is outside the focal point, okay? Greater than the focal point away. All right, now the other two, concave lens and its opposite shape convex mirror, they were both diverging devices, and therefore the image is always going to appear to be right side up. It'll always be right side up regardless of where the object is, which we'll show in a future video, and that's always going to be what we call a virtual image, okay? And in this case, the object appears to come from behind the mirror, and if you remember, in this case, the object appears to come from behind the lens because you were over here looking at it. The image is actually formed back here on the other side as your eye and your brain trace those light rays backwards. Okay, so that was a lot to go over. I hope you found that helpful. If you did, you can leave me a thumbs up in the comment section, or you can leave me a...
Okay, kind of confusing though, right? Like, I thought it was really cool though, because you guys want to be nurses, and you have to like deal with people seeing stuff, whether it's a magnifying glass or contact lenses or whatever the case is. Something interesting for you guys to all understand. Okay, so one of the questions is, a particle of light is called a photon, correct. So in Einstein's famous equation, E equals mc squared, what does the C represent? The quantum numbers of atoms involved, the number of coulombs, the number of calories of heat, or the speed of light? Speed of light, correct. Because the speed of light is C equals 3 times 10 to the 8th meters per second squared. Alrighty, this is electricity now. This is a picture of my favorite scientist, Nikola Tesla. He's responsible for inventing a bunch of cool things. I think this is, he invented Bluetooth. He did cell phones. He's done the Tesla coil, which is getting energy, so you have to use a power company. He also invented the death ray, all kinds of really cool stuff. He's a cool guy. He apparently had an affair with pigeons, fun fact. You know, that's true, that is. So, there's two types of charge that occur in electricity, positive and negative, all right? So, light charges are going to repel, and unlight charges are going to attract. So, the same thing as a magnet. Like attracts, opposites, yeah, attracts, yeah. So, Electrical potential energy is the gravitational force associated with two objects in positions. The potential difference is defined as the change in your potential energy. And then static electricity is the accumulation of extra electrons creating a negative charge. These are some of my typical definitions that you guys should kind of like memorize. Coulomb's law is a pretty important one. It says that the electric force between two charges is proportional to the product of two charges. So what that says in layman's terms is these are your charges. So what you have here is you have this Q1 and Q2. Those Q's represent charges, that's what it stands for. Your R is going to be your radius, which is R21, that just means the radius between particle 1 and particle 2. And then F1 and F2 are your forces from these charges repelling. So if one charge is doubled, the electric force is doubled. If both charges are doubled, the charge increases 4 times because it's double and double, and they're both going crazy. When the distance between the charges doubles, the force decreases by a quarter of the original force. And when two forces are brought closer together, the force is going to increase. That was something good for you guys to put in a flashcard. So for circuits. So circuits are going to be composed of 3 different things: currents, voltage, and resistance. So a current is measured in amperes, voltage is measured in volts, and resistance is measured by ohms. So a nice little picture for you guys here to memorize what's going on. So you have a current that's flowing through this wire called the amp. Your ohm is your resistance, or what's stopping that amperage from going through. And your voltage is what's the driving force, and what's pushing that current through. So this is a schematic. Don't pay too much attention to this. This is just to show you guys, show you what's going on. I'm sure at some point in life you're going to get some kind of TV schematic, and that's what this whole thing is. This is different kinds of circuits and resistors and all kinds of crazy stuff, diodes, and all of that. It's basically a recipe for how to build a circuit. And then, this is important though. So you have factors that affect resistance in a conductor. The factors that are going to affect the resistance, or that stopping force, is going to be the type of material. So iron wire have a higher resistance than copper because we know copper conducts electricity very well. Therefore, since it's conducting electricity very well, it's allowing it all to go through with low resistance. All right. The length of the wire, longer wire would have a higher resistance, so therefore you can send more energy, more current through a shorter wire than a longer one. The thicker the wire is, the easier it all is for it to go through. Looking at this little diagram over here, it'd be easier if this little guy were to fit through a thicker hole than for a smaller one. And also temperature is also going to be able to affect the resistance. Higher temperature is going to have a higher resistance. So we have another type, which is series versus parallel components. Right here you have what's called Kirchhoff's law, which is V equals IR. It's one of those famous ones that comes to circuits, which is your current is equal to, or the voltage is equal to the current times your resistance. So in a series is the same throughout each component. And the voltage is the sum of the voltage across this component over here. So your resistors are going to be added up all through here. Your voltage is going to be summed up through all these as well. And your current is going to remain the same throughout in a series. Parallel, your voltage remains the same throughout the entire thing. And your current is going to be the sum of all these, and the resistance is going to be 1 over the R1, R2. So just take a flashcard and kind of like look over all of these. I saw a couple questions on your test through these. So an example is Christmas lights. I don't know how many of you are old enough to remember back in the day when Christmas lights, when one of those bulbs in that strand went out, the entire strand went out, and it was such a pain to go and find which one went out. Nowadays, what we have many lights that are in parallel. So in parallel, since each one's considered its own individual circuit, like how you see from the schematic right over here, they're its own little body, only one of those lights go out, so you can still use that nice little strand of Christmas lights and not go through the pain of having to go find another one. So the current in a parallel battery is equal to So in a parallel, the current is going to be the current in the largest battery, the difference of the largest and smallest battery, the sum of all the battery components, or the current minus the resistance. Correct. Coming from all of this. The resistance of a wire is dependent on the following except for. So resistance of a wire is dependent on is it either length, temperature, voltage, material, or the cross-sectional area. Correct, C. Because once again, we saw the factors that are going to be dependent on resistance is going to be the type of material, the length, the temperature, and the thickness, aka the cross-sectional area. Okay? So, magnets. Magnets are fun. Okay, magnetic field over here. This is a picture of the Earth's magnetic field with the two poles, which is why we can use compasses, because the Earth is a giant magnetic pole. Okay, so magnets is a material that produces a magnetic field. It's a force of attraction, and you're going to have north and south poles. So it creates a field line around it. Like as you see over here, it would be taking in this energy from around it down over here and pushing it back up through. It kind of like creates its own energy almost. All right? And it's kind of circulated over here. What we have is, it's a really cool experiment to do if you ever get a chance to go and do it. If you take a bar of magnet and you put a piece of paper down on top of it, and you put a bunch of like lead shavings on top of it and kind of shift it out, it actually forms this. It's a fun experiment to do with kids. And this actually depicts the magnetic field that's going through this magnet over here. It's a visual representation of this invisible force. Fun, right? They exist whenever charges are moving. The overall strength is measured by a magnetic flux. Don't worry too much about that symbol. I'll never see it again. And a magnetic field is considered B, so the term we use for it is the density of magnetic flux, or the vector field. Now, more stuff you guys need to pay attention to. Electromagnets. Electromagnet is considered a coil of tightly wrapped wire. It's called a solenoid around an iron core. Whenever the current passes through the core, the iron acts as a magnet. So what they have here is a picture of what it actually looks like. So you can take a battery, and you can take a nail. You can use it at home. I don't suggest it, but you can take a piece of wire, and you can attach it to either end of the battery, and then wrap it around this iron nail. And it actually will make the iron into an electromagnet. So generators work similar to this, not quite the same. So in a generator over here, you have the north and the south are going to rotate this little inner piece, which is then going to turn something in here, which then gets converted into mechanical energy, which then gets converted into electrical energy. So the magnets that are pushing this turbine to go turn is making it mechanical energy. That mechanical energy then gets turned into electrical energy, and that's how generators work. So if you wanted to strengthen an electromagnet, what could you possibly do? Would you want to decrease the number of coils around the core? Would you want to increase the number of coils around the core? Lower the voltage, or change the core from iron to aluminum? Correct. You want to increase the number of coils. That's giving that more charge. See, because the wire is carrying the charge, maybe you get more energy around there. That's good. So what will determine the presence of a magnetic force field? A compass, iron nails, a magnet, or all of the above? All of the above. They all will actually determine a magnetic force field. All right, last section, thermodynamics. The physical properties on the molecular level. So I touched on this a little bit in the chemistry seminar if you guys came to that. But thermodynamics is going to cover a little bit of this and a little bit of that. It's not in your NLN packet from the ASC Center, I don't think at least. However, it was in the book, the NLN book under physics. So I wanted to go ahead and cover it with you guys. So thermodynamics is the branch of physics that's concerned with heat and temperature and their relation to energy and work. So we all understand this from the chemistry seminar. We have a solid, which is all compacted atoms all together. You have liquid atoms, which kind of have a little more energy to move. They're able to freely move about. You have gases. So the molecules are very far apart. They move really, really fast, and they touch each other, they collide with each other. And then you have plasma, which is at very high temperatures of the stars. So the kinetic theory of matter says that atoms and matter are in a constant state of motion. The motion and spacing of atoms determines the state of matter. So kinetic, which you remember from kinetic energy previously, which means energy in motion, this is the same kind of a thing. So the more kinetic energy or the more motion that these atoms are going to be having is going to determine their state of matter. So you have a solid, and they're vibrating, but they're vibrating super, super close together. And they don't really care much kinetic energy because they're not really moving too much. Whereas liquid, they're able to move about a little bit more freely, so they're getting a little bit faster. They have more kinetic energy. So the same thing with gases. Gases go extremely fast. They're just kind of zooming around all over the place. And they rarely ever ran into each other. So therefore, they'd have more kinetic energy. So specific heat is an important one over here. Specific heat is defined as energy needed to raise the temperature of 1 gram by 1 degree. And each specific material has its own specific heat. So it's different for everything. It's different for water, it's different for the tabletop, it's different for ice, different stuff. Latent heat is the heat energy needed to create a phase change. And this is what we call a phase diagram. So I'm going to have a video that's going to describe this a little bit more. So we have solids, liquids, and gases. This is your triple point, which is at a certain temperature and at a certain pressure, any object can be at a solid, a liquid, and a gas all at once. And that's what the triple point is called. So how you read this graph is you're going to say that at any point in time, given a certain temperature, given a certain pressure, for your specific material in question, because they're all different for the phase diagrams, you'll be able to determine what phase of matter your object is in. So a perfect gas law, it says that pressure times volume equals the number of moles times your gas constant times temperature. What does that mean? That pretty much is going to translate into Boyle and Charles' laws. So Boyle's law says that P1 equals V1 equals P2 V2. So the way the pressure and the volume are going to be changing. And then Charles' law. I don't think you guys should really have too much stuff with that for as far as the physics stuff goes and in your NLN. But just so you're exposed to it, there's that. Now, something that I saw in the questions was converting temperatures. I would make sure I would look at that. So converting Celsius into Fahrenheit and then into Kelvin as well. These are the formulas for how to convert each of these. And then it gives you examples of how to actually solve them. So it's just knowing the formulas and knowing how to plug them in. And then it's just algebra from there. And you guys should all be okay with the algebra. If you have any questions, come and see us at the ASC Center. Alrighty, another video about phase diagrams. Almost done.
A phase diagram specifies the physical state of a substance as temperature and pressure varies. The diagram consists of regions separated by lines. Each region displays the conditions at which a particular phase is stable. Each line between two regions displays the conditions at which those two phases are in equilibrium. This phase diagram is typical for most substances. In general, lower temperatures and higher pressures correspond to the solid phase. Higher P and T correspond to the liquid phase, and lower P and higher T correspond to the gas phase. Let's take a closer look at the diagram and view the various parts on the molecular level. A magnified view within the solid region shows the regular array of tightly packed particles typical of a crystalline solid. Note that the particles in a solid are not fixed, but jiggle in place about their crystal sites. A magnified view of the liquid reveals a major difference between it and the solid. The particles are still in close contact, but their positions are much less restricted than in the solid, and they roll and tumble around one another. In stark contrast to the solid and liquid phases, a magnified view of the gas shows the particles far apart, except when they collide. At any point along the solid-liquid line, the phases are in equilibrium. Melting and freezing are occurring at the same rate. In other words, the same number of particles are moving from the solid to the liquid per unit time as are moving from the liquid to the solid. Similarly, at any point along the liquid-gas line, vaporizing and condensing are occurring at the same rate, which means that the number of particles moving from the liquid to the gas per unit time equals the number moving from the gas to the liquid. Finally, along the solid-gas line, subliming and depositing are occurring at the same rate. That is, the same number of particles are moving from the solid to the gas per unit time as are moving from the gas to the solid. Two other features of the phase diagram are important. The first is that the liquid-gas line ends at a point called the critical point, beyond which the distinction between a liquid and a gas disappears. Let's close in on this point and 2 points very close by to see what this means. At a nearby point in the gas region, the gas is under very high pressure, so the particles are reasonably close to each other. Thus, the density of the gas is relatively high. At a nearby point in the liquid region, the liquid is at a very high temperature, so the particles are beginning to separate from each other. Thus, the density of the liquid is relatively low. As these 2 points approach the critical point, the particles in the gas move even closer together and the density increases, while the particles in the liquid separate even more and the density decreases. At the critical point, the densities become equal and the phase separation between liquid and gas disappears. The second important feature occurs at the junction of the 3 phase boundary lines. At this point, called the triple point, the 3 phases are in equilibrium simultaneously.
Alrighty. Okay, so time for some more questions. The vaporization of solid dry ice to gaseous carbon dioxide by heating is an example of sublimation, evaporation, precipitation, or condensation. Sublimation, correct. And the heat required to melt 1 kilogram of a solid is the heat evaporation, fusion, vaporization, or specific heat. Heat of fusion, correct. Awesome. So there's that. Just letting you guys know, so you guys with some pictures and stuff from your camera, trying to take pictures of the slideshow. This whole thing with the videos is also available on our ASC website. Once again, just go ahead and Google search ASC, IRSC. It's under test prep and under NLN. You can find the slideshow and the videos on there as well. So if you need to review anything before your test, there's that. Please come and see us over at the ASC Center. We're here to help you. For sure. We had the NLN review book as well that I was getting a lot of questions from and a lot of the extra information. So come free and check that thing out. All right. Feel free to come up with any questions. If you have the reviews, the instructor reviews, you can leave them in the back as well. Thank you guys for coming, and I hope you all do well. My little physicist now. It's awesome.